Welcome to Dr. Sherry's Astronomy channel. This time, the theme is Overturning Conventional Theories. The True Nature of W49B, a Candidate for Gamma-Ray Burst Remnants. In the universe, stars undergo spectacular explosions at the end of their lives. These are called supernovae. This phenomenon scatters new elements throughout the cosmos and creates the materials that become the source of life, truly a crucial event in the cosmic cycle. While we call them supernovae, these explosions are classified into several types depending on how they occur and the mass of the original star, each hiding different dramatic stories. Broadly speaking, there are core collapse supernovae, which occur when very massive stars, at least 8 times heavier than our Sun, reach the end of their lives, and Type 1a supernovae, where white dwarf stellar remnants explode after accumulating too much material from a companion star. Among core collapse supernovae, some of the most powerful explosions can be accompanied by gamma-ray bursts, one of the brightest phenomena in the universe. Supernovae accompanied by gamma-ray bursts release far more energy than ordinary supernovae and are thought to involve characteristic jet-like ejections of material, known as bipolar outflows. These explosions are believed to occur when the star's core collapses to form a rapidly rotating black hole, with surrounding material being ejected as jets. Such diverse and powerful explosions are thought to leave distinctive traces in their remnants, the supernova remnants. Therefore, by examining in detail the debris that spreads after the explosion, we can decipher the grand drama of what kind of star met its end through what mechanism. Supernova remnants are nebular objects left behind after supernova explosions. This image shows Cassiopeia A, the remnant of a supernova that exploded 300 years ago, captured in X-rays by NASA's Chandra satellite. From such X-ray observations, we can observe the distribution of elements scattered by the supernova and the shock waves created by the explosion. Supernova explosions supply elements formed inside stars to space, and heavy element synthesis also occurs during the high temperature conditions of the explosion. Additionally, the shock waves created by the massive energy release are sources of various phenomena such as heating of interstellar material and cosmic ray acceleration. Therefore, by studying these remnants, we can obtain clues about what kind of star exploded and trace the star's evolution. To explain supernova remnant observations in an easy-to-understand way, they are often compared to fireworks. Fireworks shine in various colors using flame coloration reactions from metals that were synthesized inside stars and scattered into space by supernova explosions. Flame coloration is when metals are held in a flame, causing the flame to change to vivid colors. For example, in this photograph, from left to right we have lithium, strontium, calcium, sodium, barium, trimethyl, copper, cesium, and potassium, each emitting distinctly colored brilliant light. Fireworks are created using these flame coloration reactions. By packing gunpowder mixed with various metals into firework shells, we can create spherically symmetric fireworks, fireworks with jet-like structures radiating from center to edge, or even heart-shaped fireworks. By looking at the shape and colors of the shining fireworks, we can imagine what metals were used and how they were arranged inside the firework shell. We expect to be able to study element synthesis and explosion mechanisms in stellar explosions, supernovae, in the same way. When considering stellar evolution, diagrams like this with concentric circles are often drawn. The star's surface consists of hydrogen, and moving inward, elements with higher atomic numbers like carbon, oxygen, neon, silicon, and iron are thought to be synthesized. However, since we cannot directly observe stellar interiors, we don't fully understand how elements are actually created. If we could measure the conditions of various elements scattered by supernova explosions, it would be like playing a video in reverse. We could estimate the internal structure of the star at the moment of explosion, bringing us closer to understanding supernova explosion mechanisms. The Chandra satellite captures the process of elements flying into interstellar space due to supernova explosions like this. The left diagram shows the X-ray spectrum, and the right shows images for each element. Elements heated by extremely hot gas above 1 million degrees, like in supernova remnants, shine in specific X-ray colors. This is characteristic X-ray emission. Looking at the spectrum, we can see that various elements are present. In X-ray observations, unlike visible light observations, we can simultaneously observe images and spectra. By selecting the energy bands of each element, we can create images for individual elements. Silicon shows this red image distribution, sulfur shows yellow, calcium shows green, and iron shows a purple image-like distribution. We know that the equivalent of 20,000 Earths worth of silicon, 10,000 Earths worth of sulfur, 70,000 Earths worth of iron, and an amazing 1 million Earths worth of oxygen, approximately 3 times the mass of our Sun, have been dispersed into space. When we overlay images showing only elements like silicon, sulfur, calcium, titanium, and iron, it looks like this. Since this shows only elemental distributions, the arc-shaped shock waves shown in the opening image are not visible. Looking at the elemental distribution, we can see that unlike spherically symmetric fireworks, it has an irregular shape. Furthermore, jet structures are visible in the upper left and lower right sides. These are the green areas. Based on such observational data, three-dimensional reconstruction is being advanced using a technique called astronomical medicine. This is a technology that reconstructs three-dimensional structures from fragmentary information, similar to CT scans used in medical practice. The diagram shown here is a three-dimensional model created from X-ray data. Purple corresponds to jets, deep green to iron, and light green to silicon, and we can confirm complex distributions that differ for each element. From these reconstructed three-dimensional models, we can see how elements were created inside the star and how they spread. Furthermore, to achieve higher precision three-dimensionalization and approach supernova explosion mechanisms, we need to precisely observe other elements and their motion. To precisely measure such elemental motion, instruments capable of measuring X-ray spectra with very high resolution are essential. This is where XRISM, the X-ray imaging and spectroscopy mission developed primarily by Japan and launched in 2023, plays an active role. This satellite carries Resolve, a special spectrometer. It precisely measures the energy, that is, the wavelength, that X-ray photons carry by converting them one by one into heat. As a result, it becomes possible to obtain very precise spectra, enabling us to capture emission lines from various elements and their motion that we couldn't detect before. Utilizing the overwhelming spectroscopic capabilities of the XRISM satellite to the fullest, observations were conducted of W49B, one of the supernova remnants that has been shrouded in mystery. W49B is a relatively young supernova remnant within our galaxy that has a distinctive morphology. While typical supernova remnants have nearly spherically symmetric shapes, W49B has been known from previous observations to have an irregular shape. Particularly, the distribution of heavy elements like iron and nickel scattered by the explosion shows an asymmetric distribution different from lighter elements like sulfur and silicon, and its formation mechanism has been a long-standing mystery. This unusual morphology suggests that W49B may have been formed through a special process different from ordinary supernova explosions. The spectrum of W49B captured by this XRISM satellite looks like this. The horizontal axis shows energy, and the vertical axis shows brightness. Blue is from the XRISM satellite, and gray is from conventional observation instruments aboard the Suzaku satellite. We can see that the XRISM satellite captures emission lines from many elements with very high precision and in great detail. What's even more amazing about the XRISM satellite is that it can acquire these overwhelming spectra along with images for each pixel of the detector. Therefore, we can capture in detail how various elements are distributed in space and what kind of motion they have. For example, this diagram shows the spectrum of iron ions in a specific region of W49B, demonstrating its high precision. By analyzing such high-resolution spectra region by region, we can determine the line of sight velocity of each element, that is, whether they are approaching or receding from Earth. This diagram shows the line of sight velocities of various elements: silicon, sulfur, argon, calcium, chromium, manganese, iron, and others. The upper panel shows the regions where resolve on the XRISM satellite created spectra, overlaid on a Chandra satellite image. The middle and bottom panels show changes in line of sight velocity for each element in the east-west and north-south directions. Particularly from comparison with iron-ion data, we found that one end of the supernova remnant is approaching Earth, the other end is receding, and the central region is not moving significantly. Integrating these observational results reveals a drum-like bipolar structure that overturns conventional theories, as shown in this diagram. While not everything about why W49B took this shape has been revealed, this observation has determined its unique three-dimensional structure for the first time, representing a discovery that opens new horizons in theories of stellar evolution and explosions. For example, such bipolar structures are thought to be formed in hypernovae, a type of explosion accompanied by particularly powerful gamma-ray bursts among supernovae. In gamma-ray bursts, when a star's core collapses into a black hole, ultra-high-speed jets are thought to erupt in both polar directions. The drum-like structure observed in W49B strongly suggests the possibility that it was formed as a result of such ultra-high-speed jets erupting from the central star and colliding with interstellar material. While we cannot definitively confirm that a gamma-ray burst occurred based on shape alone, we expect that by pursuing energy budgets and other factors, its origin will become clear. Future developments will be exciting. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.